All right, in this lesson we're going to take a look at the fundamental theorem of calculus, part 1 and part 2. And what the fundamental theorem of calculus is going to lay out for us is the relationship between this process of integration that we're starting to take a look at and the material on differentiation that we've looked at through most of this course. So for part 1 of the fundamental theorem of calculus, we're going to look at some example problems that you can use it to solve. For part 2 of the fundamental theorem, really we just want to understand the relationship between integration and antiderivatives that we looked at last week. And we also are going to, from this, develop a process that we can use to evaluate integrals that we're going to be using for the rest of the course. So let's just take a minute here and we'll remember where we are here. We started, the whole motivating question here was how do we find the area under the curve? Okay? And we had developed this method where we take our function, our continuous function f at x that is defined from a to b, and we divide it up into a bunch of little tiny rectangles, and we calculate the area of all of these rectangles, and then we add up all of these areas to get an estimate for the area under the curve. And we noticed that this approximation would get better and better if we increased n, the number of rectangles, and ideally, if we took the limit as n goes to infinity, we would get the exact value for the area under the curve. And this was so important to us that we developed this formulation here for this limit as n goes to infinity of this sum of all of these, of the areas of all of these little rectangles. And we called this our integral here, so the integral from a to b of f at x dx. And this represented the area under f at x from a to b. Now, we've got some nice symbol there to represent the area. We still don't have a good method for evaluating that integral or evaluating that sum when we're taking the limit as n goes to infinity there. So we're going to back up a little bit, and we're going to take a slightly different look at how we can approach this area problem here. So we've got our function f at x. We want to find the area underneath it, and we're going to define this thing that we're going to call an area function. Okay? A is a function of x. And A as a function of x just represents the area under this curve, f at x, from a to x. And x is just some value over here. We can move it, we can make it larger, we can make it smaller. And as we change the value of x, that red line is going to shift either left or right, and it's going to change the value of a at x, the area under the curve. Okay. So this function, if we were to write it explicitly, using the notation that we've been developing, we could think of a of x as the integral from a up to x of f at x dx. Just knowing that this integral symbol so far just means the area under the curve from some starting point to some ending point. And what makes this a function is that we have let our ending point here be a variable. Okay? As x changes, the area under the curve is also going to change. Okay? So we could even summarize something like, for a positive function, okay, f at x always greater than 0, as x increases, a at x increases. Okay, so a at x is basically like an area accumulating function. We accumulate area under the curve as we increase x. Make sense? Okay. Now, we'll start with a very, very simple example of applying this concept to a function. We've got a linear function, f at x equals 2x plus 1. And what we want to do here is we want to find the area under the curve from 1 to 3 first. Then we'll find an area function representing the area from 1 to whatever value of x that we want. And then for some strange reason, we're going to take the derivative of that function that we find. So let's start with part A here. if we want to find the area under this curve from 1 to 3, and this is the region that we want here. This is the area. Okay. This is actually just a simple geometric figure. Okay? It's a trapezoid, kind of like what we used in the trapezoidal approximation in the last unit. So if we're going to find the area of this thing, let's, it's a trapezoid. So our area is just A plus B times H divided by 2. Formula from way back there in grade 9. So what we need are, I mean, this trapezoid is tilted on its side, right? So the height is going to be this distance from here to here. Our height is 2. Our top height is going to be this distance right in here. So this is A equals, looks like 3. And B is going to be sort of the length of the bottom if you tilt it 90 degrees. That's going to be, looks like 7. Okay? And this value of 3 and this value of 7 are just given by the value of the function at 1 and at 3. So we can plug those numbers in. What do we get? 3 plus 7 times 2 divided by 2 works out to 10. So we know that if we're thinking of this in terms of our area function, A at 3 is equal to 10. Okay, when we set the end point of our area accumulation function at 3, we get a value of 10. Okay, now let's go ahead and try part B here, where we find a general function that we could use to calculate the area underneath this line for any value of x. We're going to approach this the same way. Okay? We will have our starting point here at x equals 1. We'll put our ending point just at some random place called x. And we can still approximate this, well, actually calculate it exactly using a trapezoid. So our width here, from there to there, is going to be given by whatever the value of x is minus our starting value. So x minus 1. Our height over here is the same as it always was. It's going to be 3, because that's not going to change. Our height over here is going to change as we change the value of x. So this is just going to be given by f at x. Now what is f at x? It's 2x plus 1. So our area function, which kind of like the integral from a to bx of f at x dx, we can write it out explicitly as this trapezoid formula here. So we want to add 3 and 2x plus 1. We want to multiply those by the height, which is x minus 1. Divide all that by 2. Okay, and now let's simplify this. So we get 2x plus 4, x minus 1, all over 2. Expanding this out gives us 2x squared minus 2x plus 4x. It's plus 2x minus 4 all over 2. X squared plus x minus 2. So that would be our area function for a function 2x plus 1. And just to make sure that this works, we know that when we sub in x equals 3, we should get 10. So if we sub in 3, we get 9 plus 3 minus 2, which is 10. Okay. Blah, blah, blah. We're just doing grade 9 math again with some functions thrown in here. What's the point? Well, what happens when we take, remember this part C we were going to do, find the derivative of the area function. The derivative of this function is 2x plus 1, which is our original function. Surprise, surprise. Okay? So it may not be a surprise to you. It's like, yeah, we've been doing derivatives all year, and this kind of makes sense. But why would you expect a connection between, the area of this trapezoid we found and derivatives? We use derivatives to find the slope of the tangent. What's going on here? So, and maybe it only works in this one very, very specific case. So here's what we want to, here's the thing. We have found that the derivative of the area function is the original function. Is this always true? It'd be kind of nice if it is, because then when we're trying to find the areas of things, it's possible that all of the stuff that we've been doing on derivatives might actually come in handy. Okay? So that's our next step. We're going to show that this is always true. So let's try to show that the derivative of our area function is always equal to this original function, f at x, that defines the curve that we're trying to find the area under. Okay, so we've got our function here. We've got our starting point a, which is not going to change. We've got our endpoint x. And what we're going to do is we're going to investigate what happens if we move that x value by just a tiny, tiny, tiny little bit. Okay, so I'm going to move it just over here like this, from x to x plus h, because we use h to represent just a tiny little change in something, right? So as x goes to x plus h, the value of our function, f at x, is going to change to f at x plus h, and the value of our area function is going to change as well. Instead of a at x, we are now calculating a at x plus h. So the area that we've added, or what we've added to our area accumulation function, is this tiny little red strip in here. Okay. So let's call that thing that we've added delta A. Okay? The change in area. So the change in area, as we go from x to x plus h, is going to be the area at x plus h minus the area at x, just the difference in those two areas. Okay. We'll call that expression number 1 here. Now, I've got one expression here for delta A, that area. We could also do what we did when we were doing approximate integration, and we could try to estimate the size of that red rectangle there by approximating it with a rectangle. So we will approximate delta A with a rectangle. is going to be approximately equal to, well, let's see. What is the height of that rectangle? Well, let's say it's approximately f at x, the sort of the left end point of that rectangle. And its height, or sorry, its width is the amount that we changed x by. So its width is just going to be h. Now, this is an okay approximation. Okay, the approximation gets better as we take the limit as h goes to 0, right? As we make that thing smaller and smaller, there's less of a sort of a curvy bit up at the top, so our rectangle approximation gets better and better. Okay, just like when we're doing areas under curves, the smaller our rectangles, the better our approximation. What we're trying to find is the derivative of our area function. Now, we don't know how to find the derivative of something. What do? We go back to first principles. So let's take the limit as h goes to 0 of a at x plus h minus a at x all over h. Now, we have an expression for a to the x plus h minus a to the x. That's up here, number 1. That's just delta a. So this is the limit as h goes to 0 of delta a over h. We have an approximation for delta h, which is our rectangle. Let's put that in instead. So this is approximately going to equal to f at x times h over h. And that approximation is good if we take the limit as h goes to 0. And because we're already taking the limit as h goes to 0, this is acting in our favor. How do we evaluate this limit? Well, we can cancel off the h's. We get the limit as h goes to 0 of f at x, which doesn't depend on h. So it's just f at x. So the derivative of our area function from first principles is the original function. Okay? This is the first part of the fundamental theorem of calculus. Okay? If you have a function, f at x, which is continuous on some interval, we should call that interval I, and a is in that interval, then if we define a function, capital F at x, as being the integral from a to x of f at t dt, then the derivative of f at x is going to be f at x, or the derivative of this area function is going to be that function. Okay. So it also implies that f at x is continuous and differentiable on the interval. Continuous. On that interval I. So if we've got some function, capital F at x, whose derivative is f at x, this is just another way of saying that f at x, capital F at x, is the antiderivative of small f at x, which means if we take the derivative, okay, instead of writing f primed, I write d by dx of f at x. I still have f at x. And if I put in the definition here for capital F at x, which is the integral from a to x of, sorry, I switched over to t's, didn't I? F at t dt, we get this. Okay? So the derivative with respect to x of the integral from a to x of this function f at t is equal to the original function, which is really just saying that if you take the derivative, then you integrate, those two processes cancel each other out. Okay? And that's what the first part of the fundamental theorem establishes. The differentiation and integration are actually inverse operations. Now, you may have suspected this, but there's no reason why that should be the case. I mean, differentiation came about because we wanted to find the slope of tangents. Differentiation came about because we wanted to find the slope of tangents. Integration came about because we wanted to find the areas under the curve. These are two different geometric problems. Why are they connected together? Fundamental theorem of calculus says that they are. Integration and differentiation are inverse processes. Okay, one last thing before we get to some examples here. What's with the t? Why did I suddenly throw a t in there? This is the way that the first part of the fundamental theorem is usually written. Okay, what is our variable here? X is the variable. T is what we might call a dummy variable. All right. And we kind of stick it in there so we don't confuse it with the x. Okay? If we used x's everywhere, it wouldn't be as clear to us what the x actually means. So keep in mind the picture of these functions as sort of the area accumulation thing. Imagine you've got a function, f is a function of t, which is graphed with an x-axis starting at 0 and going up to t, and x is some point on this graph, which we can change, move left or right, that determines where we stop taking our area. Okay? So t is used to define our function here, but x is the thing that we're actually changing here when we're doing our integration. Okay? It's like kind of like x is a particular value of t.